Now, besides the use of binary variables in our previous example, let me give you 4 more special ways in which we can use binary variables in our constraints. And what are they? Well, first, we have functions with m possible values, and let me explain them one by one later in more detail. Second, we have either-or constraints. Third, we have k out of m constraints. And fourth, we have fixed cost and fixed benefit scenarios or constraints. Now, for function with m possible values, let me give you one very quick example. Let's say we have a constraint x1 plus x2, and let's say x1 plus x2 should be equal to either 1 or 4 or 70 or 100. Now, in this very simple example, you have a function x1 plus x2, but this function actually has 4 possible different values. x1 plus x2 can be equal to 1 or 4 or 70 or 100. Now, what we'd like to do is we'd like to retain the idea of this constraint, but use the concept of switches, the on-off switches or binary variables, so as to make this constraint linear. Essentially removing the word or in the constraint. Now, in order to introduce switches here, what I'd like to do is to convert this constraint x1 plus x2 into a constraint where the right-hand side is equal to 1, but I will be adding a variable, let's call it y1. And then instead of having or, I will be adding 4 and then y2, again or, plus 70 y3 or 100 y4. And then as you can see, we shall put here y1 plus y2 plus y3 plus y4 should be equal to 1, and yi should be binary. Now, as you can see, the original constraints idea is that this function x1 plus x2 can be equal to 1, 4, 70, or 100. So you have to look for a way to allow x1 plus x2 to be equal to 1, 4, 70, or 100. And how do we do this? We use the concept of switches. So the idea is you place one switch, one on-off switch for every possible value here. So you have y1, y2, y3, and y4. y1, if we were to define, is the switch for 1. y2 is the switch for 4, y3 is the switch for 70, and y4 is the switch for 100. And what are we trying to do with, or what are we trying to say with this constraint? What we are trying to say is that out of the 4 switches, we only want 1 to be on at any point in time. This one just tells us that every variable y is a switch. And as you can see, if only one variable y is equal to 1, and obviously the rest are 0, then what will happen is this function x1 plus x2 will either be 1, 4, 70, or 100. If y1 is equal to 1, then x1 plus x2 is equal to 1. If y2 is equal to 1, then it is equal to 4. If y3 is 1, then the right-hand side is 70. If y4 is 1, then the right-hand side is 100. Okay, for either-or constraints, let me give you another example. Let's say we have 2 constraints, x1 plus x2, and let's say x1 plus x2 should be less than or equal to, let's say, 1000. And then let's say you have another constraint. You have 2x1 minus 3x2, and this one, let's say, should be greater than or equal to 50. Now, if we have these 2 constraints in our linear programming model and nothing else, then I think we can fairly assume that we are intersecting the 2 constraints. Why? Because if you read the constraints, let's say we read these 2 constraints, you have x1 plus x2 less than or equal to 1000, and 2x1 minus 3x2 greater than or equal to 50. And let's say you have your non-negativity constraints. x1 greater than or equal to 0 and x2 greater than or equal to 0. So what am I saying? What I'm saying is that when you write constraints in your linear programming model, they are naturally intersections of each other, no? With an invisible ampersand and operator and. Now, what if we remove the ampersand, we remove the operator and replace them with the word or? So what do I mean by this? What if you have these two constraints, however, in your linear programming model, only one of them should be active at any point in time? It's either x1 plus x2 should be less than or equal to 1000, or 2x1 minus 3x2 is greater than or equal to 50. And that is the premise of an either-or constraint. Okay, let me give you graphically a different example that will show this either-or constraint. So let's say I have my y-axis, x-axis. Let's say this is 4. Let's say this is 4 again. Let's say this is 2. This is 2. And let's say I have this line. I have this line. Okay, and I have this line as well. Okay, now let's say for this diagonal line, it is facing downwards. This horizontal line is facing upwards, and this vertical line is facing to the right. Now, if we were to come up with a linear programming model here and intersect all three constraints, if you remember your graphical solution method, this diagonal going down, vertical going right, horizontal going up, the intersection actually is just this corner point. Now, what if your feasible region is actually composed of these two small triangles? Okay? What is the set of constraints that will come up or that will form the feasible region that is composed of these two triangles? Now, this diagonal line is an x1. Let's assume this is x1 and this is x2. This diagonal line is an x1 plus x2 less than or equal to 4. No? You have the diagonal line, and it's a less than or equal to because it has to be facing this way, facing towards the origin. This vertical line is an x1 greater than or equal to 2. Okay? And this horizontal line is an x2 greater than or equal to 2. However, if you wanted to have a feasible region that is composed of these two small triangles, technically, x1 plus x2 less than or equal to 4 should always be on. However, x1 greater than or equal to 2 and x2 greater than or equal to 2 should be either or constraints, and therefore should have the operative word or. Why? Because look, you have your x1 plus x2 less than or equal to 4 going this way. If x1 is greater than or equal to 2 and this third constraint is off, then you have this line going to the right, you have this diagonal line going this way, you form this constraint, this feasible region. Therefore, this feasible region is composed of these two constraints. On the other hand, if this is on and this is on, okay, so you have x1 plus x2 less than or equal to 4 going this way downwards, and you have x2 greater than or equal to 2, you have this going up. Therefore, the intersection is this triangle. Therefore, this gives us this feasible region. And therefore, if you have these three constraints where these two constraints are either or, then you will be able to form this set of feasible region. So, going back to the previous example, how do we now handle either or constraints in your linear programming model? Why? Because having the operative word or here makes it nonlinear. Okay? This will not be allowed under linear programming assumptions. So, what we need to do right now is to understand how we will use the concept of binary variables or the concept of on-off switches to turn on and turn off constraints. In the previous example, you are turning on and turning off values, constants. However, for this example, you need to turn on or off constraints, an entire set of constraints. Now, before giving you the answer, let me give you two usual answers that are always given to me, but these two answers are both incorrect. Okay, let me show you the first incorrect answer. And hopefully, this is obvious for us why this is incorrect. Okay. One incorrect answer is by multiplying y1 to both sides for the first constraint and multiplying y2 both sides to the second constraint. And then stating that y1 plus y2 is equal to 1 and y1 comma y2 are binary. Okay? Now, let me explain why this answer is incorrect. If y1 and y2 are binary variables and you created the constraint that says y1 plus y2 is equal to 1, then what you're essentially saying is you can only have one of the two variables, y1 and y2, to be equal to 1. If y1 is equal to 1, then y2 is equal to 0, and vice versa. Now, if y1 is equal to 1 and y2 is equal to 0, this becomes 1. So this becomes 1. This also becomes 1. So multiplied by 1. This becomes 0. This becomes 0. So what will happen is this constraint will become x1 plus x2 less than or equal to 1000. This constraint will become 0 greater than or equal to 0. And if the other scenario happened, meaning y1 is equal to 0 and y2 is equal to 1, then what will happen is the first constraint will become 0 less than or equal to 0, and the second constraint will become 2x1 minus 3x2 greater than or equal to 50. Now, as you can see, if y1 is equal to 1, then this happens. If y2 is equal to 1, then this happens. Isn't this technically correct? Because this is actually what we want to happen. We're allowing y1 to be equal to 1 or y2 to be equal to 1. If y1 is equal to 1, then technically this constraint is on. If y2 is equal to 1, then technically this constraint is on. Now, I do understand that yes, technically it is correct. However, the main problem lies in the fact that you multiplied a variable y1 in this case, and y2 in this case, two variables. So you're technically making your answer nonlinear. And that is why even if the result of this model is technically correct, because if y1 is equal to 1, then you have this case. If y2 is equal to 1, then you have this case, which is what we actually want. But multiplying y1 to x1 and x2, y2 to x1 and x2 made the model nonlinear. Now, let me show you the second way in which you can answer this incorrectly. I will have x1 plus x2 is less than or equal to 1000 but I will multiply the right-hand side with a binary variable y1. And then, in the same way, I have 2x1 minus 3x2 greater than or equal to 50. And again, I will multiply the right-hand side with the binary variable y2. And then we have the same set of constraints as we had a while ago. We have y1 plus y2 equals 1, and y1 and y2 are binary. Okay, now, because of these two constraints, then what we are saying is y1 can either be 1 or 0, y2 can either be 1 or 0, and if one is 1, then the other is 0. So let's look at the case where y1 is 1 and y2 is 0. If y1 is 1, then this becomes x1 plus x2 less than or equal to 1000, which is good because that is our first constraint here. However, because y1 is 1, therefore y2 is 0, and because y2 is 0, then the second constraint becomes 2x1 minus 3x2 greater than or equal to 0. And I think we can stop here. Why? As you can see, if you just multiplied the constant part, the right-hand side with the binary variable, yes, if y is 1, then you have the correct right-hand side as seen here. You have this x1 plus x2 less than or equal to 1000. However, the other binary variable which will become 0 actually made the right-hand side, the entire right-hand side, 0. Which means if y1 is equal to 1 and therefore y2 is equal to 0, we have this. Unfortunately, we cannot accept this answer because technically, this is not even part of the original problem. Where in the original problem, where you have this first constraint or the second constraint, where in the original problem is this? It's not existent. In fact, you just added this new constraint because of this assumption. If you want to continue, then if y1 is equal to 0, and y2 equals 1, then what do you have? You have x1 plus x2 less than or equal to 0. You have 2x1 minus 3x2 greater than or equal to 50. Yes, this constraint is present in the original problem, but this first constraint is the problem. This is a technically a new constraint that was added. And that is why multiplying the right-hand side with a binary variable y1 and y2 separately and stating that they can only be 1 or 0 and vice versa is technically not correct. Now that you've seen the two ways in which you can incorrectly answer this problem, let me now show you how to correctly convert this either-or constraint into a model that is linear, and yet it still retains the idea that if you have these two constraints and you want them to be on only one at a time, meaning if this constraint is on, the other one is off, and vice versa, what we need to do right now is to understand how do we actually turn off constraints. How do we turn off constraints? And let me explain that in this manner. Let's say this first constraint, being it being a less than or equal to constraint, let's try to understand this right-hand side, this 1000, to be your daily allowance in school. Okay? Now, if you have an allowance of 1000, I doubt that usually is enough for us whenever we go to school and eat at JSEC or eat at Katipunan. Okay? Now, the question now is, what will make you remove or not have a constraint in terms of your allowance? Right now, your allowance is 1000. What will make you turn off your constraint? Paano mawawala yung constraint? Let me give you an idea. What if, so let me write again the constraint. So this is your budget. What if I gave you 100 pesos? Will you still have problems with your budget constraints in terms of your spending in school, spending in restaurants in Katipunan, etc., etc.? Will you still have problem? Most probably. Let's say I'll give you 500 additional. I think you will still have problems, right? You will still complain, kulang. Okay, so kulang yung 500. Let's add 1,000. Baka kulang pa rin, no? Maybe. Let's say MVP came to Ateneo and saw you and gave you 1 million pesos additional to your weekly allowance of 1,000. Do you think you will still have any problem with regards to your budget, no? Titipid ka pa sa pagkain sa JSEC, sa Katipunan? Most probably hindi na. Why? Because I think this 1 million added to your original daily allowance is big enough so that you will not feel the budget constraint anymore. And that is the idea of turning off a less than or equal to constraint. What you do is you have your original right-hand side and you add something very big. Okay? You add something very big to it. Now, given that logic, how do we now turn off a greater than or equal to constraint? In order to understand that, we need to understand first what this right-hand side is. What is this 50? We can look at it as some requirement. So let's say 50 is a passing grade. Let's say, no, for math, 50 is your passing grade. So your grade on the left, no, for your left-hand side should be at least 50. And that is your constraint, your grade constraint. Now, how will you turn off or how will you not feel this grade constraint anymore? If I subtract 1 from the requirement and make it 49, will you still have the constraint? Maybe, no? Especially if the topic in math is very hard, no? 50 is not far from 49 and you might not still be able to reach 49. What about 10? I do heard of some math tests that are very, very hard, or some OR tests that are very, very, very hard, wherein the average long test score is even less than 40. No, so I doubt reducing 50 down to 40 by subtracting 10 is enough to remove your constraint. Let me exaggerate. What if I remove 1 million? In this case, if your left-hand side is your grade and the right-hand side becomes negative 999,950, I doubt you can do anything here that will still make your left-hand side be less than negative 999,950. So what is the lesson here? The lesson here is if you remove or you subtract a very big number from your right-hand side requirement, no? And why is this a requirement? Because this is a greater than or equal to constraint, then you can technically turn off your constraint. So turning off a constraint does not mean multiplying a switch on the right-hand side. Turning off a constraint means either adding a very big number or subtracting a very big number depending on your constraint. If your constraint is a less than or equal to constraint, then you need to add. You need to make your right-hand side very, very big so that whatever the right-hand side is, it doesn't matter. It seems like if your right-hand side is a very, very big number, then that is a supply value, And if that is if your supply is a very big number, then you won't have any problem with that. In the same manner, if your right-hand side is if your constraint is a greater than or equal to constraint, therefore your right-hand side is a requirement, something that you need to reach, and if you subtract a very, very big number, then I doubt you will have a hard time reaching this. If you will not have a hard time reaching this, then I doubt you have you will have this constraint as on. Okay? So in the end, how do we now handle either or constraints? So you have x1 plus x2 less than or equal to 1000. You have 2x1 minus 3x2 greater than or equal to 50. And as explained a while ago, to turn off a less than or equal to constraint, you add a very big number. Now, I will instead of writing 1 million, I will just use the letter big M. Okay? So what is M? M is a constant. It is a very, very, very big number. Okay? Now, I don't need to put here an exact value. What I just need to understand is M should be big enough so that when I add M to the right-hand side, it will turn off automatically. Okay? In the same way, to turn off a greater than or equal to constraint, I will subtract a very, very big number. Okay? And from here, this is how I will introduce the concept of either or. You multiply M with Y1, you multiply M here with Y2, and then you have your Y1 plus Y2 equals 1, and then Y1 and Y2 are binary variables. So as you can see, if Y1 is 1, then this becomes 1. M gets added to 1000, therefore constraint 1 is off. So let me define that so that it's clear. Y1 is binary. If Y1 is 1, then constraint 1 is off. This one is otherwise. Let me define Y2. Y2 again is binary. No? And if Y2 is equal to 1, what will happen? M gets subtracted to the right-hand side 50. Therefore, the second constraint is off. Therefore, constraint number 2 is off. Otherwise. Thus, what we have is an either-or constraint in a linear fashion. So as you can see, looking at the resulting model, it is linear. Now, for number 3, we will be discussing K out of M constraints. Let me clarify what K out of M constraints mean. In the context of your either-or constraint, your either-or constraint is actually 1 out of 2 constraints to be active. So in general, K out of M constraint is just a generalization of your either-or constraint, and therefore we can use the technique that we use in either-or to handle K out of M constraints. So let me give you an example. Let me give you 5 constraints. Let's say x1 plus x2 less than or equal to 5, 2x1 minus 3x2 greater than or equal to 6, negative 3x1 plus 2x2, let's say equal to 10, negative x1 minus x2 greater than or equal to 7, and then let's say 3x1 plus 4x2 is equal to 8. And let's say out of the 5 constraints, so out of the 5 constraints, you want 3 to be active. Now, if you want 3 constraints to be active out of the 5 constraints total, then we can use the concept of turning on and off your constraints in the previous example. Let me write here the definition of our binary variable before. let y sub I in general be equal to 1 or 0, 1 if constraint I is off, and 0 otherwise. Okay? Now, if we were to use y sub I here, then how do we turn on and off our 5 constraints? Remember, if you have a less than or equal to constraint, all you have to do is add a very big number. So I will multiply that with y1. For a greater than or equal to constraint, we will subtract a very big number, and we will multiply it with y2. Now, we weren't able to discuss equality constraints, and in this case, I don't think simply adding or subtracting an m will turn on or turn off your constraint. Why? If you look at your equality constraint and your right hand side is a constant, whether you add an m or subtract an m, and let's say you multiply this with y3, then if y3 is 1, then you're adding m to 10, and because your constraint is an equality, you're just technically creating altogether a different right-hand side. In the same way, that will happen also if you're subtracting a very big number. So technically, you don't add a very big number, you don't subtract a very big number to turn off your equality constraint. So how do we turn off a constraint, an equality constraint? What you do is you split the equality constraint into 2. What do I mean? An equality constraint is technically the intersection of your less than or equal to 10 and greater than or equal to 10. Remember? Because if you have this less than or equal to 10 and this greater than or equal to 10, if you get the intersection, you get the equality constraint. And now that you've converted your equality to inequality, there is a way for us to turn off inequality constraints. So your less than or equal to 10, we can add a y3. Your greater than or equal to 10, we can subtract a very big number. But because we want to turn off both constraints at the same time, then this also has to be y3. For the fourth constraint, we just have negative x1 minus x2 greater than or equal to 7 minus my4. For the fifth constraint, we have an equality constraint, so we split it into 2. We have 3x1 plus 4x2 is less than or equal to 8 plus my5. 3x1 plus 4x2 greater than or equal to 8 minus my5. And then, what we have are your other constraints. y1 plus y2 plus y3 plus y4 plus y5 equals something. We will discuss this. And then you have your yi between 1 and 0 and integer. Now, in the either or scenario, we added all the binary variables and equated it to 1. Why? Because in the either or scenario, you have 1 out of 2 constraints to be active. And remember, if y is 1, the constraint is off. So if you want 1 out of 2 constraints to be active, you are also saying 1 out of the 2 is also inactive or off. Therefore, in the either or constraint, when you added y1 plus y2 and you equate it to the number of constraints to be off, the right-hand side is 1. However, in this case, because we have 3 out of 5 constraints active, therefore, this means 5 minus 3 are inactive or off. Which means the sum of y1, 2, 3, 4, and 5 should be equal to 2. Or, in general, this has to be m minus k.